In this lecture, we'll discuss the topic of buoyancy and stability.
First, let's try to understand what the buoyant force is, the force that causes something to float. So if we have an object submerged in a liquid, the pressure, as we know, is going to vary according to the depth. The pressure is greater at a greater depth. So let's imagine the object is placed at a depth of S and it has a thickness of H. So the pressure on top of the object is going to be rho G times S times the area of the top. The pressure on the bottom is going to be greater. It's going to be greater by a factor of H, the thickness of the object. So if you calculate the net force on the object, it's going to be the force on the bottom minus the force on the top. So if you subtract those, what you end up with is the density of fluid times G times H times A. So, but what is this? This is simply so A is the area, H is the thickness of the object. That's the volume. So what this term represents is the volume of the volume of the water that's displaced by the object. So rho G times that volume, that's simply the weight of the liquid displaced by the object. So the net result is that the buoyant force acting on the object is equal to the weight of the liquid displaced by the plate. So this leads us into what's known as Archimedes' principle, which says that the buoyant force acting on a body immersed in the fluid is equal to the weight of the fluid displaced by the body. It acts upward through the centroid of the displaced volume. So here we have an object that's submerged, and so the buoyant force, the magnitude of it is going to be equal to the weight of the fluid displaced by the solid, and the direction is going to be upward through the centroid of the object. So let's take a look at objects that float. So for floating bodies, the weight of the entire body must be equal to the buoyant force, which is the weight of the fluid whose volume is equal to the volume of the submerged portion of the floating body. So in this case, if it floats, the only part that we're concerned about is the volume that's underneath the water. The weight of that volume is going to be equal to the buoyant force. So if you set an equilibrium where the object's floating, the buoyant force, the upward force, is going to equal the weight. So you can end up with a relationship where the volume of the submerged part divided by the total volume of the object is simply a ratio of densities of the body compared to the fluid itself. So if the fluid's water, you just use the density of water. Now you kind of have to be careful of this because notice the top it says the density of the average body. So if you have a solid piece of steel, well then the density is is going to be uniform. But if you take that steel and you pound it out into thin sheets and fold it up and make a steel ship out of it, even though the density of steel is greater than the density of water, it'll still float, because what you've done is you've taken some of the overall volume that was steel and made it into basically air, right? So you talk about the average density. So you kind of have to be careful using this formula. You can get steel objects that float, right? You can get steel ships that float. But if you have a piece of solid steel, well then yeah, it's going to sink to the bottom. Now there's another case where you have an object that sinks and doesn't go over the bottom. If it's equal to the density of the fluid, well then you end up with what's called neutral buoyancy, where the object will remain at basically where you put it under the water. It won't sink or rise. Then, of course, if the density is greater than the density of fluid, well, then the object will sink all the way to the bottom. So the book talks about how you measure density. Well, one object you can use is what's called a hydrometer. The hydrometer consists of a hollow glass tube that is weighted at one end. So here shows a picture of a hydrometer. It's got little weights at one end, and it's hollow. And it's got liquid in it. So if you put this hydrometer in pure water, well then it's going to float up to a certain level, and basically what you do is you mark that as like the specific weight of water. And then that you use that as kind of a gauge. And so if you put it in any other kind of liquid, it's going to rise or fall depending on what the density of the liquid is. So if it's, it depends on the specific weight relative to the water. If it's, it'll sink lower or sink higher depending on if the density of the fluid is greater than or less than water. So let's take a look at this example 218. So here we have a 135 pound container that's 2.5 feet wide and 6 feet long. So it goes into the board, into the screen, 6 feet. The total depth of the or height of the container is 1.5 feet. So here we have two cases where you put the weight inside of the container. So this part here is air, right? In here, so you put the weight inside of there, and it's going to sink down to a certain depth. So in part A, we want to find what that depth is, and then part B, we want to take the weight out and suspend it below the container, and then we want to find out what D prime is. Is this going to be less than or greater than D? And the problem he says take the specific weight of steel to be 490 feet per cubic pounds per cubic feet, and the specific weight of water to be 62.4 pounds per cubic feet. So for part A, this part here, so what you have, for equilibrium, if this thing is going to float, you have to have the weight of the block plus the weight of the container has to equal the buoyant force. And if those are equal, it'll sit there and float, and then you can calculate what D is. So we're told the weight of the container, it's 135 pounds. We're told the weight of the block, it's 150 pounds. Remember, the buoyant force is going to be equal to the weight of the volume of the water displaced. And so here, it's going to be the density of water times the 2.5 feet times D times 6 feet, because it's 6 feet into the board. So 2.5 feet times 6 feet times D, that's the volume of water that's displaced by the container, and then you multiply by the density of water to get the weight of the water displaced. So when you work this out, the only unknown here is D, so you can solve for D. It turns out it's 0.304 feet. So what does that mean? Well, if the total ship height is 1.5 feet, that means that D is less than that, so it floats. And that's really the only way you know it's going to float or not, is you have to compare D to the depth of the ship. If this D would have came out to be 1.7 feet, well then obviously it didn't float, it sunk, right? So let's work part B. So in part B, you take the weight out of the container and you let it hang below the container. So in this case, you really got two things going on. You have the weight of the container and the weight of the weight, and you have to worry about the volume of the water displaced by the container. But now you also got water that's going to be displaced by the weight itself. So you got two buoyant forces. You got a buoyant force pushing up on the container, and you got a buoyant force pushing up on the block. So you got to take these into account. So again, it's an equilibrium problem. Sum of forces have to be zero. So if you sum those forces, you take the forces going down as negative, the forces going up as positive, the two buoyant forces. It's similar to before. Here's the weight of the container. Here's the weight of the block. This is the weight of, the buoyant force of the container. It's the density of the water times the volume of water displaced by the container. So it's 2.5 feet by D prime by 6 feet. D prime we don't know, that's what we're trying to find. Now, but also we have to consider the volume displaced by the block. So that's going to be equal to, so we got to find this volume. So the volume of the block is simply going to be the weight of the block divided by its density. So we have to take that into account in the second part here. So we got the 150 pound block divided by its density, steel. That's going to be the volume of the block times the specific weight of water. So this will be the weight of the volume of water displaced by the block. And so all that has to equal to 0. So when you solve for this, you get d prime is 0.284, which is certainly less than the 1.5 feet, so it still floats. So notice it floats higher, right, because d prime is a little bit less than d. So let's talk about stability. So an object can float in a liquid or gas in three different kinds of conditions. It can be in stable equilibrium, unstable equilibrium, or neutral equilibrium. So how do we distinguish between the three? So let's take the first case of stable equilibrium. So if you put a bar in a liquid so that its gravity, its center of gravity is below the center of buoyancy, this will be stable equilibrium, because how do you demonstrate that? Is you take this bar, if you hit it slightly so you displace it from its equilibrium, it actually is stable, sets up this couple force where the buoyant force is going to push up, the weight's going to push down, so you end up getting a stabilizing couple moment that will right this bar back up to where it's supposed to be. If you push it over the other way slightly, it'll do the same kind of thing. Let's look at the other case of unstable equilibrium. That's a case where the center of gravity is above the center of buoyancy. And in that case, if you push this, it'll set exactly straight in the water. It'll stay where it's at. But any kind of force to push it over will cause it to destabilize, and it'll basically flip around. That's an unstable equilibrium kind of situation. Neutral equilibrium is when the center of buoyancy and the center of gravity are exactly the same place. In that case, if you hit the object, it'll basically turn and stay where it's at. It just remains in its location. It doesn't try to right itself or flip back over. That's a case of what's called neutral equilibrium. So let's spend a few slides talking about ship stability. So when you have a ship that floats, you're going to have, again, you'll have the weight of the ship is going to act through the center of gravity, and you're going to have the center of buoyancy. But when the ship turns, or is rocked by waves, the center of buoyancy and the center of gravity are not going to line up along the same line. So here they were both kind of lined up on the same vertical line. On the case where the ship is hit by a wave, the center of gravity is obviously going to act straight downward. The center of buoyancy is going to act straight upward. And if you tilt it over the other way, what you'll notice, if you run the line of center of buoyancy all the way to the top, and you flip it over and you push the ship over the other way, the center of buoyancy will actually cross at a point up above the center of gravity, which is called the metacenter. So the metrocentric height is the distance between the center of gravity and this metacenter, which is again the intersection point of lines of action of the buoyant force. So the length of this distance between M and G is a measure of the stability of a ship. So ship designers try to make this distance as large as possible. The bigger the metacentric height, the more stability of the object. So the bottom line is if the metacenter is above the center of gravity, then the object will float in stable equilibrium. And if M is below G, well then the body is unstable. So what happens a lot of time is, so if a ship's just staying straight, with no rocking action to waves, everything's fine, everything lines up fine. But when we have a normal condition where the M is above the center of gravity, well, if you hit by a wave, it just kind of rocks back over itself. So here the case where M is here and G is there, so you end up getting this restoring force where the gravity is trying to turn the boat clockwise, and the buoyant force is trying to turn the boat clockwise, so it'll stabilize itself. But if you get a case where, like this kind of condition, where M is below G, well then the problem is that the gravity is trying to turn the boat counterclockwise, and the buoyant force is trying to turn the boat counterclockwise, and so you end up in a case where this boat will flip upside down. So this happens a lot if you have flooding or something in a container. You have an accident at sea. You bring in a lot of water, you can physically make this side heavier than that side, and so it can affect the metacentric height of an object. So let's take a look at problem 2-120 out of the textbook. This is one of the homework problems. A solid ball is made of plastic having a density of 48 kilograms per cubic meter, and it's tied to with a rope to the bottom of the tank. So we want to determine the tension in this cable AB if the ball is submerged at the depth shown. So this shows that it's 0.9 meters from the top of the water line to the top of the ball, and the ball has a 0.6 meter radius. So again, here this is an equilibrium problem where the sum of forces equals 0. So you have three forces. You got the weight of the ball acting through the center of gravity. You got the force of buoyancy acting through the center of gravity, and you got the tension in the rope. Tension and weight are downward, buoyancy is upward, so you can set up a simple relationship. Remember this, the buoyant force is equal to the density of water times G times the volume of the submerged object. The weight is equal to the density of the object, which is the plastic, G times the volume of the ball, minus the tension in the rope. So the only unknown here is the tension in the rope. You can solve. Plug in the different conditions you're given here. Remember, so this is it's a ball, so it's a 4/3 pi cubed. So in this case, you got water, and you got the ball here. Subtract, you get 8.45 kilonewton is the tension.